Hello, and welcome to Linear Algebra. This is Lecture 6. Today's topic is linear maps. Okay, so last time, we talked about vector spaces. For example, Rn, or Fn, where F is an arbitrary field, are vector spaces. And we saw another example, solutions of a homogeneous system of equations, of linear equations. Right? So as we've mentioned a few times already, everything in this class ends up coming back to solutions of systems of linear equations. Okay, so that's what we talked about last time. This time, we want to talk about maps between vector spaces. Okay, so let me preface our discussion by saying that one of the great insights of 20th century mathematics is that to properly understand a structure, such as a vector space, or the structure of vector spaces, what we need to study are the maps that preserve that structure. So, linear maps. This insight goes by the name of category theory, which you may have heard before. Okay. So in our particular case, the structure of a vector space is given by vector addition and scalar multiplication So we're interested in the maps between vector spaces that preserve this structure. Okay, so formally, let V and W be vector spaces over the same field. A function T from V to W is a linear map, or linear transformation, or linear operator. These terms are interchangeable. So it's going to satisfy two properties. It's going to take vector addition to vector addition, and it's going to take scalar multiplication to scalar multiplication. So first, we call the first property additivity. And this says that for any two vectors in the first vector space, T of V1 plus V2 is equal to T of V1 plus T of V2. And the second property we call homogeneity. And this says that you preserve scalar multiplication. So this says for every vector v in V and scalar A in the field, T of A times V is equal to A times T of V. Okay. If you have a map like this, we refer to V as the domain of T and W as the codomain of T. Okay, the set of all linear maps between two fixed vector spaces, V and W, is denoted curly L of V comma W. If V is the same as W, then we abbreviate. L of V to mean L of V comma V. Okay, so we can use this to make a point I talked about a bit last time. So we can use linear maps to recognize that two vector spaces are really the same vector space. So let's consider our example from last time. T, let's take an arbitrary field F4 to the 2x2 matrices with entries in F. Actually, let me go ahead and mention that same convention. If you have 2x2 matrices, then you often just write the 2 once. Okay, so the map is going to be, you give me a column, A1, A2, A3, A4, and I will assign to it the square with entries A1, A2, A3, A4. Okay, so this is the same map we talked about last time. And I mentioned last time that vector addition and scalar multiplication are going to give you basically the same result, just written in different form, regardless of which vector space you're working with, right? So a more formal way of saying that is that this map T is a linear map. So T is a linear map. So let's check that. So we need to check two things. We need to check additivity and we need to check homogeneity. So to check additivity, we need to find what is T of the sum of two vectors. So let's say the first vector has entries A1, A2, A3, A4, and the second vector has entries B1, B2, B3, B4. Okay, well that's the same as T of the vector with entries A1 plus B1 dot dot dot. Well, let's write them out. A2 plus B2, A3 plus B3, A4 plus B4. And so that is the matrix with entries A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4. On the other hand, if we had started with T of the vector A1, A2, A3, A4, and then added to it the image of the vector B1, B2, B3, B4, this would have given us first the matrix A1, B1, A1, A2, A3, A4, and then the matrix B1, B2, B3, B4. And when you add those together, you would get A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4, right? So check, we got the same answer. And then we have to check homogeneity. So to check homogeneity, let's say we take T of C times the vector A1, A2, A3, A4. Okay, well, like before, what we do is just go ahead and do the scalar multiplication inside. So we get CA1, CA2, CA3, CA4, and then apply T. So we end up with a matrix CA1, CA2, CA3, CA4. And then we notice that is C times the matrix A1, A2, A3, A4, which is C times T of A1, A2, A3, A4, just like we wanted. Okay, so that shows that T is a linear map. Now, having a linear map lets us compare the two vector spaces. But in fact, in this case, it's really the same vector space, just written in a different way. So let's write that out. So this lets us compare these two vector spaces. What shows that they are the same, let's put the same in quotes, is that T has an inverse. Right, so it's an inverse map, S, which goes from 2 by 2 matrices to F4, that is also linear. Right? And that is very easy to write down. S starts with a matrix, entries A1, A2, A3, A4, and returns the column A1, A2, A3, A4. Okay, S and T are mutually inverse. That is to say, S of T of U is equal to U for all U in F4, and T of S of W is equal to W for all W's in 2 by 2 matrices. Okay, we really care about this sort of map, so we give it a name. An invertible linear map is called an isomorphism. Okay, so a linear map is known as a morphism between linear spaces. And so a morphism that shows that two things are the same is an isomorphism. Iso meaning same. We say that two vector spaces are isomorphic if there is an isomorphism between them, right? And when we say that they are the same, really what we mean is that they are isomorphic. So that means that as far as the vector space structure goes, they are indistinguishable, right? So of course, if I give you a column with 4 entries, or I give you a 2 by 2 square, you can tell that they're different because, well, one is square and the other one's not, for example. However, if all you're looking at is the vector space structure, then they are the same vector space. They are indistinguishable because we have this isomorphism between them. Okay, of course, not every linear map is an isomorphism. So here's an example. Consider the map T from F4 to F2 given by, so you give me a column with 4 entries, and I will just keep the first 2 and ignore the other ones. A1, A2. This is linear. I will let you check that that is a linear map, but not invertible. Right? And that's really easy to see. So for example, if you have 0, 0, anything, anything, that gets sent to 0, 0. So this map cannot have an inverse because it's not injective. There are many vectors of the form 0, 0, anything, anything. Okay, here's another example. For any vector space, V, the identity map, I from V to V, which just takes a vector V and gives you back the vector V, is linear, and in fact an isomorphism, which is a pretty trivial statement. Okay, but it's a very important linear map. Here's another example. Let's do something more geometric. You don't have to have a formula written down as long as you can say what the map does. So for example, reflection across a line in R2. Or for example, a plane in R3. It's a linear transformation. Okay, so we're going to try to convince ourselves of this geometrically. Right, so let's draw this. Let's say that that's the line. So then if you have a vector here, then you end up with this vector over here, call it RV. Okay, so additivity. Okay, so say that's the line. Oh, I should have said, in this case, you want to reflect across a line that goes through the origin, or a plane that contains the origin. Okay, so in this case, we might want to have different colors. Oh, sorry. Okay, so let's say that here is the vector v, and so here is RV, so that's v, and this is RV. And then let's say that here, let's say that that is the vector w. So, okay. Sorry, let me start over so I can draw something closer to be intelligible. So let's say that that's the vector v. So that's RV. Let's say that that is the vector w. So there is R of w, roughly speaking. So then if I do v plus w, that's going to be like doing this vector w over here. So it's going to look like that. This is v plus w. And then if I do R of v plus R of w, that would give me a vector that looks like that. R of v plus R of w. And if you draw this carefully, you see that this is also what you get from doing R of v plus w. Okay, so that picture, properly drawn, is meant to convince you of additivity. Homogeneity is an easier picture. Okay, so say that that's the line. Let's say that here is the vector v. Then here is the vector 2 times v. If we reflect the vector v, we get something like this. So let's say that that's r of v. So then if you do 2 times r of v, you get something like this. On the other hand, if you do r of 2v, then this is exactly what you get. So these are equal, and that's the property of homogeneity. Okay. Excellent. So let's do another example. Okay, this is a very important example. We'll see in some sense that as long as you're working with finite dimensional vector spaces, we haven't talked about what that means yet, but most of you have already seen some notion of dimension. So if you're working with finite dimensional vector spaces, then every linear map, in some sense, is one of these. Okay, so let's say you have a matrix. Where I goes from 1 to m and j goes from 1 to n. So this is an m by n matrix. Well, let's say with coefficients in field F. Okay, then A acts as a linear operator, right, or linear map, linear transformation, however you want to say it. It's a linear operator between Fn and Fm by matrix vector multiplication. Okay, so here's how that's defined. If the vector v, right, so I'm going to start with a vector in Fn, I'm going to end up with a vector in Fm. So let's say you give me a vector v in Fn, so I have n entries in the field. Then I'm going to define A times v. This is going to be a vector in Fm, right? So I'm going to have m entries. These are going to be sum j goes from 1 to n of A1 j v j. These are numbers. Dot dot dot. Sum j goes from 1 to n A m j v j. Right. So I have one entry for each row of A. Right. So I end up with the same number of rows. Of rows as A had. All right, so for example, let's say that the matrix A is a rectangle, A, B, C, D, E, F. And okay, so this is a 2 by 3 matrix. So in particular, I have 3 columns. So I need my vector to have 3 entries. So let's say V1, V2, V3. Then A times V is going to be AV1 plus BV2 plus CV3, and then DV1 plus EV2 plus FV3. Okay, so notice I started out with a matrix that had 2 rows, and I ended up with a vector that had 2 entries, right? So if this is in F3, this is an element of F2. Okay, so a couple things I want to mention. So first of all, note the sizes. Right, so we have A, V, and then A times V. So A is a 2 by 3 matrix. V has 3 entries. In order for this to make sense, we need for these two to coincide. And then it's like once they coincide, they cancel. And so you end up with something with 2 entries. Also, remember the convention for naming a matrix was that you went down and then to the right. The convention for multiplication is that you multiply like this. So you take this row and you multiply it by this column, right? This is the dot product that we're used to from working in Rn. So this, here I have 3 entries, here I have 3 entries, and how do I multiply them? Well, you just multiply one entry with the corresponding one and then add, right? And that's how you get the entries here. Another thing to mention is that the vector AV is a linear combination of the columns of A with coefficients given by the entries of V. Right, so notice in this example, this column appears here, just multiplied by V1. This column appears here, multiplied by V2. And this column appears here, multiplied by V3. So this is true in general. If we write A1 for the first column, A2 for the second column, up to AN for the last column, this is the matrix A. And then we have the vector V with entries V1 through Vn. Then the matrix vector product is equal to the sum, j goes from 1 to n, with Vj as coefficient and Aj as vector. Right? So the vector AV is a linear combination of the columns of A. Okay, using this, it's easy to see that matrix vector multiplication is linear. That is to say, we get a linear transformation. So to check that a map is linear, remember we need to check 2 things, additivity and homogeneity, right? So let's check additivity. A times V plus W would be, thanks to the formula we just wrote down, this would be V plus W, Vj plus Wj, multiplying the jth column of A, right? But that is just the sum of Vj Aj plus the sum of Wj Aj, and that is A times V plus A times W, right? Which is what we want to check. And similarly, for homogeneity, we need to check that A of a scalar multiplication is a scalar multiplication of the image of A. So A of C times V, well, we can write that as the sum, j goes from 1 to n, of the entries of C times V, so CVJ, as coefficients in a linear combination of the columns of A. And then we can pull out the C, Vj Aj, and that is C times A of V. That's what we want to check. Okay. Another thing to notice, let's say you take a very simple vector. So this is a vector we're going to call Ej. So this is an En. So Ej is the vector in Fn with a 1 in the jth coordinate and zeros in other coordinates. Then A times V, right? So A times EJ is just the column AJ, the jth column of A, right? And that's just plugging in right here. If all of these numbers are 0, except for one of them, and that one is the jth one, then, or let's say here, since I'm using J to count, let's say it's the kth one, then in this sum, the only one of these terms that survives is when this Vj is the kth one, right? All the other ones are 0, and you just end up with Vk, Ak. But Vk is just the number 1, and so you just end up with the column A sub k, right? Here's another example. Let's say that you take the matrix like this. So you have zeros almost everywhere, but every row has a 1 somewhere. And those 1s are in different columns. Well, in this case, let's say the vector v has entries x, y, z. Then A times v, this is easy to compute, right? So you would do this row times this column, and so you would get y. If you do this row times this column, you get z. And then if you do this row times this column, you get x. Right? So in this case, multiplying by A, all it does is it takes whatever vector you had and it rearranges the coordinates. Right? So this shows that rearranging coordinates is a linear map, and in fact, any reordering of the coordinates is a linear map. Okay, here's another example. The n by n identity matrix I sub n is an n by n matrix with entries in a field, whatever field you want, right? Because every field has zeros and ones. And this is the n by n matrix with ones on the diagonal and zeros elsewhere. Right? So all you need are zeros and ones to make this. So this looks like this, in, so it would have 1, 0, 0, 1, dot, 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 zeros, dot, 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 zeros, dot, 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 zeros, dot, 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 zeros, dot, 1. Right? So a much easier way of writing that, we'll write diagonal 1, comma, dot, 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 1. Right? So when you have a matrix that has zeros everywhere except on the diagonal, except possibly on the diagonal, then we just abbreviate that by saying diag and then writing out the diagonal elements. And we call it the identity matrix because as a linear map, we have in times a vector equal to that vector for all vectors in Fn, right? So this is really easy to check, but I encourage you to check it to practice working with the definition of matrix vector multiplication. Right? A similar thing is the action of any diagonal matrix is easy to figure out. So if A is a diagonal matrix with entries d1 through dn, right? So let's write that out in this case. So this would be d1, 0, 0, d2, like dot, dot, dots, zeros, dot, dot, dots, zeros. And then ends with dn. Then as a linear map, A times the vector v, let's write out the coordinates of the vector, V1 to Vn, all this does is it multiplies each entry by the corresponding element of the diagonal. Okay, so this is a really easy map to understand. All we're doing is scaling each entry by the corresponding scalar on the diagonal. Okay, now let's go back to what we talked about the first class, the example from ancient China. So revisiting the example from ancient China, right? So remember this one was the equation 3h plus 2m plus L equal to 39, and then we had the equation 2h plus 3m plus L equal to 34, and then we had h plus 2m plus 3L equal to 26, right? So we have this system of linear equations. So notice now, we can recognize this. Let's take the coefficient matrix, 3, 2, 1, 2, 3, 1, 1, 2, 3, and the vector HML. And notice that if you do this vector, this row times this column, you get exactly this left-hand side. If you do this row times this column, you get exactly this left-hand side. And if you do this row times this column, you get exactly this left-hand side, right? So this matrix vector product is the left-hand side of this system. And we're just trying to solve that equal to this, right? So we recognize this as AX equal to B, as long as this is what we mean by A, this is the vector X, and this is the vector B. Right? So in general, we can write any system of linear equations concisely as a single matrix vector, well, actually vector valued system. It wouldn't be a system, it would be a single equation. So as a single vector valued equation in this way. Right? So specifically, if the system of equations you start with is like this, A11, X1, etc., until you get to AM1, X1, let's say MN, XN equal to BM, right? This system, this is the same as taking the coefficient matrix times the vector with entries x1 through xn and setting it equal to the vector with entries b1 through bn, bm. So this would be A, this would be X, this would be B, and this is the system AX equal to B. Notice here that A is an m by n matrix, X is a vector of order n, and like we said before, these two have to match in order for the matrix vector product to make sense, and if they do match, then it's like they cancel off, and you end up with a vector of size, the remaining letter. Okay, so everything comes back to system of linear equations. Matrix vector multiplication lets us write a linear system of equations as a single equation. It's a single linear equation, except that now our coefficient is the coefficient matrix. Okay, excellent. And we will stop there and pick it up from there next time.